fascinating direction for these sorts of tools, in that there really had not been any other method that could address contacting these things and teasing them out to make measurements. We learned a good deal through the images as well, although the mechanics was sometimes difficult to discern because the forces were so very small in terms of unkinking and unfolding and finally stretching out of these sorts of aggregate structures. And we studied carbon nanocoils that came from Japan, from Nakayama's group. And this was quite interesting. There's nothing particularly fascinating about the mechanics here. It's pretty straightforward. But what was interesting is that these coils from the mechanical measurements and then more carefully SEM imaging at higher magnification, we ended up realizing that these are actually nested coils. So they're typically two coils directly adjacent to each other, or three. And you might possibly see that here. So it was the mechanics that we measured in the model that we used that allowed us to go back and look more carefully at the SEM images to find out that was the case. So this is the same sort of approach where we're using this EBIT to make clamps and to stretch these coils and fit the mechanics in terms of the standard coil mechanics model. And then to do better SEM to discern and TEM as well. These coils were actually nested with each other. So I'll stop here, and next I'll go into nanotube ribbons and flattened tubes and twisted tubes and shell sliding tubes in the next lecture. Have any questions about this? Yes.
Have you considered using iron-induced deposition to make the clamps?
Which type of deposition?
Iron deposition.
Iron?
With a focused iron beam.
Ah, that's a great question.
Or with the irons.
Yeah, it can be a valuable technique, but the only problem with that is that the typical ions that are used, as you're probably aware, are gallium, indium, etc.
Yeah.
So there's an interesting paper that Jayan had published with Edison, and only later was it realized that there were portions of the paper that was wrong. It was a very nice paper. It was an early paper in which they used ion beam-induced deposition of tungsten to write tungsten lines on a long multi-hole carbon nanotube and make multi-probe measurements to look at the electrical properties. It's one of the first papers along that line. And then later it was realized that the spillover effect from the ion beam had actually damaged the multi-wall carbon nanotube shells substantially. So one of the challenges with ion beams, and perhaps it's also happening with electron beam, we don't know, is that you can be knocking out atoms in the structure that you're trying to do the deposition on.
Yeah.
So you know this very well, but for the rest of the audience,
Yeah, sure. But has it been done? Or?
Well, people have tried that, and I don't know that it's being extensively used with mechanics because I think there's the perception that EBIT is a gentler method. Yeah. And so that people who are quite expert on the ion deposition method will forcefully tell new people who don't have experience with it, when you're depositing, you're etching at the same time with the spillover. And we did ponder whether we could somehow be doing chemistry, for example, in nanotubes. Now, you may be aware from both theoretical treatment from Marvin Cohen and Stephen Louie in terms of calculating energetics, and then experimental work by David Woodsey when he was at University of Pennsylvania as an electron microscopist. Now he's dean in Northeastern, no longer doing science, but by both the theory and experimental work in making a new diaphragm and so on, the knockout energy for carbon atoms, if you say single-wall carbon nanotubes, is around 86 keV or so. So I don't know the implications of a 5-electron-volt electron hitting a graphene sheet. I'd love to have some modeling on that in terms of what we were doing and whether we were damaging our tubes while we were making our deposits. I think that there's a reasonable chance that we were influencing tube structure perhaps a ways of making lamps we consider, that I think people should consider, are shadow masks, where you might be depositing gold, which has no tendency to react with carbon at all. Gold and carbon are completely invisible, as are silver and some other metals as well. So that could be one option. Other question?
Did you ever look into defects that would reach between two adjacent walls?
In other words, something like chemical stitching?
Yeah, something like forming structure in here that would allow you to cause the motion of one of the nanotubes inspecting the other because it's different.
It's a great idea. We don't know how to create those sorts of
It's like we give you a theory. Isn't that if you were given to me the defects, it would
one of the challenges.
give me my transmission conditions.
One of the challenges with tubular structures, because of the topology, unlike graphite or those platelets that we talked about yesterday with fluorination, it's something about heating and being under stress and compression and growth and formation and a lot of sp3 bonds between the layers, is that if you have a jelly roll structure, then you can interpolate. Of course, it's not then nested tubes. And stitching layers is straightforward because we're not constrained. But if you have concentric shells, the ability to move radially is highly constrained because of the high stiffness and drive chemistry.
Move that radially, try to pull one, keep the other fixed.
The problem of cross-link, I think that is
Yeah,
cross-link, I think that is well studied in the relationship.
Right at the edge, or with
Not just the cross-link for transmission between for low transmission between different nanotubes. There is a paper published in Nature Material by Spinoza that addresses this issue even with molecular simulation.
So you're saying sort of pucker this down a bit and that up.
Suppose that you clamp the outer shell.
Okay.
And then they pull the inner shell. Then van der Waals forces would give you some sort of an axial strain.
Yeah, I'll talk about that in the next talk.
That can be modeled perfectly with formula.
And it's
Explicit formula.
And it has been.
Yes.
It has been, yeah. So it's actually a fascinating issue that ties in with Quan Ji Zhang's interest in sliding and not having the AB lattice match.
Depends on how the nanotubes have been modeled.
Yeah.
There are many ways of doing
Sure,
this.
no, I'm not saying that they modeled it perfectly. It's been modeled.
Yeah, of course, yes.
You might improve on the model.
Sometimes it's idea, but
Yeah, you might improve significantly on the modeling.
but
I think the original models assume things that are perfectly rigid.
one of those forces would give you one type of transmission conditions between adjacent walls. But if there were defects going across,
Yes.
then you would have something like a hard transmission condition rather than a soft transmission condition. That ties with the two.
I'm gonna overlap your question in some ways that I hope will interest you in the next one.
Well, if you consider elasticity, in order to reduce the stress concentration of the lamp, also you have to use a softer material. I don't know what does
And then use a longer.
goes longer.
Sure, we thought about these things too, yeah. We spent a lot of time thinking about them and never
Reach the goal.
devoting probably enough time because we were using these opposing cantilever tips, which are quite challenging to then layer with shadow masks or dot bits of epoxy and so on. That's why I think I'm sort of giving you a historical perspective because we were first, but not necessarily best, clearly. I think the best approaches are to use the MEMS-based stages that people are inventing and using and have nice flat platforms and significant regions to do things like create long clamps and so on.
I don't know if it is a problem over the long time because you are not mentioning sliding failure. You were mentioning fracture lamps. It's due to stress concentration. So if you
That's what we saw with the single wall carbon nanotubes that I mentioned. We always carefully measure the length. We carefully did before and after they were always the same.
No, I understand it, but you mentioned that you have a problem in good clamp for inside test on single wall and tubes. So
Well,
this is the difference.
not
If you
really.
increase the length,
Yeah.
if you increase the length of the clamp, this is not very significant because we are talking about the fracture of the clamp, so due to stress concentration, not to slide.
And if you have a 1 nanometer object, I don't know how much it helps to taper the clamp.
Tapering the clamp.
It's worth modeling.
Yeah,
Suppose we
yes.
have this sort of situation, and this is residing on our groove tip, and we put some clamp material here. Okay, fine. This is 1 nanometer band. Then we change the profile.
Yes.
Do this. That's not easy to do.
I
It's 1 nanometer. It doesn't mean it's not worth trying.
It is similar to a material that is softer. The tapering has the same effect from an elastic point of view. Consider a softer material.
Well, you know, Jim has explained that he has even better control over the single wall fragmentatives. There were some ambiguities in assignment N&M, you know, maybe 70% of them unambiguously assigned, no doubts at all. So we'd be happy to take advice about some of the material and try to use it in the future.
I have to send a paper, a published paper, materials related, quite recently, related to the shape for the maximum local stress in the course.
Now, yeah, maybe everyone is not aware, and so I encourage you to look, for example, for articles by Boris Stepholson and others on the pathway to failure if you have an armchair tube versus, say, a zigzag tube versus something in between in terms of its chirality. So it's quite fascinating. I mean, in one type of tube, you have some bonds that are aligned with the tensile loading direction, so you get lower strengths just because of the geometry. And in the other case, you have bonds that have to rotate, form a 5-7 defect. And then interesting things happen with those defects in terms of their motion and coalescence into larger defects that can lead to failure. So this is why measuring as a function of chirality and diameter, or equivalently, the indices N and M is so interesting. So if you don't happen to know where these indices come from, if I draw the graphene lattice and then draw the unit vectors that involve taking N steps along one unit vector, M steps along the next, and connecting that coordinate onto that coordinate to make a tube. And so that's a unique indice that gives you what magnitude you have. And N&M should strongly connect with the mechanics, and we have been able to do those experiments successfully in terms of fracture. And so that's still a great challenge. Maybe some of the students here will be the first to do it. So we're going to revisit it after 5 years. I mean, back at the top of Jim Home from Columbia, because they now can sort them perfectly. This great ice gathering technique through new methods of growth that don't have them bundling up, but well separated from each other. Yes?
Yeah, actually, yesterday you mentioned how you can make very relevant tubes.
Yeah.
Now discovered that
Same year.
in this case, plan probably become lesser machine. For very long tubes, especially made a single wall nanotube,
Yeah.
centimeter long,
Yeah.
the clamp is really issue.
I don't know why that would be.
You can use centimeter larger ones.
Oh, yeah,
The
yes.
softer material, yes.
Try to distribute the stress
How to distribute it
very
all
much.
over.
Okay.
But if it's not too small, the
I
problem
was
is
reading,
Yeah.
soft reading specialized.
So I encourage, I really encourage some modeling, just even if it's some trivial, you're going to publish a short communication for these. Other questions? Yes.
I would like to discuss another issue regarding the force measurement. How reliable can be such a measurement in your device or even the new devices, the MEMS devices?
What sort of force resolution can we
Yeah.
trying to look for some force.
be safe by using this difference of the countries that you in order to get precise measurements?
There are issues in terms of whether it's actually in the plane, the imaging planes, the SEM, slightly in or out of focus. Also, we addressed the influence of nonlinearity and published a paper on that with a theoretical colleague. So if you're dramatically warping, I'm not going to break this big, but you get beyond the point where you're in a linear regime. And so we addressed that. And I can tell you that there are some very nice papers by colleagues, such as Charlie Lieber's bending of carbon nanotubes on aluminum disulfide substrate, where we felt their analysis was not entirely apt because they were bending well beyond the linear regime and extracting the superlinearity. Good questions. Other questions? So this paper has, I think this paper now has something like 1,500 citations. So if you want to search forward, you can find all the brilliant mechanics that's been done at better stages.
You mean the science paper?
Yeah.
1,000.
1,000. Now we come to Minfeng used Zen ability to find ribbons in samples that are mostly non-ribbon, which was very amusing to me. I began to kind of joke around with Minfeng about this. Ribbons here, ribbons there, ribbons everywhere. Okay, so what happens when we look at nanotubes and we find out they're not really cylinders, which probably is not surprising to you, but was a surprise to me when I was confronted with some interesting data. So I have a friend who is an electron microscopist at DuPont, and due to a collaboration at the time when I was in the molecular physics lab at an institute near Stanford called the Stanford Research Institute, DuPont had wanted to work on carbon nanotubes. They were very active at the time in carbon fiber research, and they sold it out to Conoco. But before they sold it, they were extremely interested in nanotubes and the implications for fiber material. So I began to work with Schaefer, and I visited Wilmington, Delaware, on the other side of the country. And we were sitting next to each other, taking images, and we saw this very unusual structure. Now, what we typically saw would be just tube A by itself without this neighboring tube next to it. So we would see multiple carbon nanotubes with N shell, straight lines in the TEM image on one side and N straight lines, and that would be an N wall 2 with a certain inner diameter or outer diameter. But this one, actually, it took me about a month looking back at SRI on and off, and I finally figured out what was going on. So at first, this was just a very strange object. We didn't even know if it was nanotubes or not or something else. We just didn't know what it was. And then I realized, well, you know, it's obvious. It's a 12-walled tube, A, butted up against a 10-walled tube, B. And I hypothesized that the darker fringes, and if you look at the Nature article correctly instead of my PowerPoint, I think you'll see it a little more clearly, but unfortunately this was 1993, and we didn't have CCD cameras as our detectors, we had photographic film, and so on, and we used a densitometer. In a moment I'll tell you how. So if everything could have been done digitally, it would have been simpler, but that wasn't the case. But I can tell you that in regions, you know, this set of fringes here, compared to the outer fringes, was significantly darker. So there was the question of why are the fringes darker? And then what we did is we used densitometry, and I mentioned how we used densitometry to get thickness of individual graphene oxide sheets to you yesterday. But densitometry could also be used in a scanning mode to scan across these fringes and develop peaks, and then to carefully measure with respect to the standard that we used that day fringes and learned that the outer fringes were separated by this delta difference compared to the separation between the inner fringes. Okay? And this is the densitometry done with a scanning tool that we happen to have at SRI. Now, we have published another article in Science that was a lot of fun because we encapsulated these lanthanum dicarbide particles inside of supergiant fullerenes. And so those were conveniently in the same sample. And so we had a wonderful crystal to use as our distance standard, significantly better than, for example, gold nanoparticles that were typically used by 10 microscopists in the early 90s. So you try to deposit these gold particles and have them close by so you can zip over to one, grab a set of fringes, and then that interlayer separation would be your standard. But it turned out that lanthanum dicarbide had many, many more fringes across a longer distance, and so it was a better standard than the gold particles, and it allowed me to extract those sorts of delta differences through this scanning technique. And you can see again here that the fringes, in fact, in the center are significantly darker in the sense that they have much higher magnitude or intensity than the outer fringes. So not a perfect technique, and not so easy because we couldn't move around the image digitally and so on, but still very useful for extracting that information that I just told you. So I then hypothesized that what was going on is that there was some flattening where the two tubes were touching each other because of the van der Waals force, the adhesion force. In other words, these were compliant radially, and they were probably deforming. And we brought Jerry Tursoff into our collaboration, and he couldn't do a 12 wall or a 10 wall at that time, but he could do a double wall against a double wall. And so I can tell you that discussions with Michael O'Keefe, who's one of the world's experts in translating TEM images into structures, it's very challenging to actually do that mapping perfectly. And so Jerry just calculated the integrated atom density, but not claiming that's exactly mapping to the TEM data that I showed you. But due to this flattening, if you imagine the electron beam coming in this direction, you can imagine that the center fringes would be darker. And it turns out that that delta difference was very well picked up with this double wall tube against double wall tube as well. And so you can imagine that as these compress, there's actually a pressure here that pushes the layers a little bit closer together, and bulging of the layers here causes them to separate a bit more. So this was the first case of the first discussion of nanotubes not being perfectly similar, because it was very shortly after the discovery of the Pugno's team, and so everyone was representing nanotubes being perfect cylinders because that was the useful way to talk about their transport properties and so on. I then challenged Jerry to do the self-consistent, infinite single-wall carbon nanotube crystal. And this was a lot of fun because I think you can imagine it's a function of diameter. The smaller diameter ones are much more rigid, so the faceting that will develop in a three-dimensional crystal might be quite small. But once you get out to, for example, roughly 4 nanometers in size, you get this strong faceting. So we published this in '94, 1 year after the Nature article with the 12 wall against the 10 wall. And 6 or 7 years later, I got a telephone call from Sumio Ijima. And he said, I was both heartened and somewhat disappointed to see your theoretical article because we've now got an image that exactly maps. And so they happened to grow some bundles that had larger diameter single-wall carbon nanotubes in cross-section 10. I was attempting to download it this morning and I couldn't. Some problem, I have a new laptop, so my apologies, but it's a nice paper, and I'll get that paper and I'll put it on the CISM website. But it just looks exactly like this. And so this happens. Now, if you neglect mechanics, not that anyone decides, but people can go in some funny directions. And so at that time, around 94 or 93, people were extremely excited about very large diameter single-wall carbon nanotubes for storing hydrogen. You know, and they completely neglected mechanics. It wasn't a part of their training. And they didn't think about this faceting happening and how you'd be limited in some sense. In fact, be prone probably to under shear, complete collapse at some diameters. So there were some interesting but probably outlandish claims about using 50 nanometer single shell tubes for storing hydrogen in some sort of post-macro range. Now I'd like to talk about Min-Fung finding different collapsed nanotubes and then some interesting things that happen in terms of thinking about interlayer forces. So this was one example where we had multi-walled carbon nanotubes and we dispersed them in 2-butanol, in particular solvent. It was a good dispersant, and Min-Fung had an aptitude for finding ribbons, even though they might only be a 10% of the overall sample. So what we did in this case is we deposited multi-walled carbon nanotubes onto a substrate that we had created trenches and mesas in. And Min-Fung found this example of a ribbon, a very beautiful example, and that caused us to think about how this ribbon structure might have happened. So this is a more standard multi-walled carbon nanotube that is not fully collapsed. It might be partially collapsed due to adhesion with the surface. But this multi-walled carbon nanotube here, abruptly, at this step edge of the trench, I should say at this edge of the trench, collapses. And then traverses over here, and then it's actually so compliant that at the AFM imaging we were doing, about 1 nanonewton of loading, it actually deforms strongly downward. And then traverses over here, and the first time Min-Fung found it, it was not collapsed after crossing multi-walled carbon nanotube A, but then when he came back, I think it was 1 month later, it actually had progressed to collapse another 120 nanometers. So that was sort of fascinating. So we don't know whether this ribbon was prone to collapse during synthesis. So maybe in creation, at the very high temperatures of the carbon arc method that was used, where these are part of a cathode growth. Carbon builds up on the cathode, and you have 2 opposing carbon rods, graphite rods. Or whether they happen to collapse partially in the 2-butanol, or whether they were partially or not collapsed and then